Hi everyone! In this video, we are going to solve a problem about the Otto cycle. Here's our problem. Consider an ideal Otto cycle with a compression ratio of 5. Initially, the air is at a temperature of 22 degrees Celsius and a pressure of 100 kilopascals. During the compression process, the air receives 350 kilojoules per kilogram of heat in a constant volume heat addition process. We need to determine the A. The pressure and the temperature at the end of the heat addition process, B. The network produced, C. The thermal efficiency, and D. The mean effective pressure throughout the cycle, taking into account the change of specific heats with temperature. Listing all the given, we have R, or the compression ratio, equals to 5. The pressure is 100 kilopascal. The temperature is 22 degrees Celsius. And the Qin, or the energy input, is 350 kilojoules per kilogram. So what are we going to calculate in this problem is the pressure and temperature at the end of the heat addition process. So looking at our PV diagram, we know that these points 2 and 3, this process is the heat addition process, and the end of this process is at this point, at state 3. Therefore, for A, we are solving for the pressure and temperature at state 3, and B, the network input, the network produced, C, the efficiency, and D, the MEP, or the mean effective pressure. So let's solve for the pressure and temperature at state 3. To solve for the pressure and temperature at state 3, we first need to solve for the values in the process 1 to 2. So for process 1 and 2, we have these values for state 1. The temperature is equal to 22 degrees Celsius, or equal to 295 Kelvin. And the pressure for state 1 is 100 kilopascals. And at a temperature of 295 Kelvin, we can see the other values for state 1 at table A-17. And we will have VR equals 647.9, and our internal energy is 210.49 kilojoules per kilogram. So now that we have the values for our state 1, we will now solve for the values in state 2. So for state 2, we have this equation, V sub R2 over V sub R1 equals V sub 2 over V sub 1. So note that V sub 1 over 2 is equal to the compression ratio, and V sub 2 over 1 is equal to 1 over the compression ratio. So therefore, we will get V sub R2 over V sub R1 is equal to 1 over R. Now, plug in the given value, we will get V sub R2 over the V sub R1, which is the 647.9, equals the 1 over the compression ratio, which is 5, and we will get 129.58, and this will be our V sub R2. Now that we have the value for our V sub R2, we can now solve for the temperature at state 2. And we can find the value of the temperature at state 2 at our property table at table A-17. Looking at our property table, we see that our VR is between these points, between 127.0 and 133.1. So since our VR is between 2 points, we cannot directly find the value of our temperature at state 2. So to find the value of our temperature at state 2, we'll use this equation. M minus T over B minus T equals M minus T over B minus T, where this M, the M on the left side is this M is the middle temperature, minus the top temperature. The B is the below temperature minus the top temperature. And the M on this side is the middle VR, or the V sub R, our value, minus the top VR over below VR minus the top VR. And looking at our property table, we can see that our temperature is at these points. So plug in this into our equation, we'll see that our middle VR is the temperature at state 2 minus the top temperature, the 550 over the below temperature 560 minus the top temperature 550 equals our middle VR, the 129.58 minus the top VR 133.1 over the below VR 127.0 and minus the top VR, which is 133.0. And calculating, we will get temperature at state 2 is equal to 555.77 Kelvin. And this will be the value of our temperature at state 2. And we can also solve the value of the internal energy at state 2 using the same equation. And we will get temperature at state. Internal energy at state 2 is equal to 401.22 kilojoules per kilogram. Now that we have the value for our temperature at state 2, we can now solve for the pressure at state 2. To solve for the pressure at state 2, we'll use the combined gas law equation, which is the P sub 1 times V sub 1 over T sub 1 equals P sub 2 times V sub 2 over T sub 2, where P is the pressure, V is the specific volume, T is the temperature in Kelvin. So, since we are solving for the pressure at state 2, we rearrange this equation and we will get P sub 2 equals V sub 1 times T sub 2 times P sub 1 over V sub 2 times T sub 1. And since V sub 2 over V sub 1 is equal to 1 over R, therefore V sub 1 over 2 is equal to R. And we will get P sub 2 equals the V sub 1 over V sub 2 will be equal to R. So R times T sub 2 times P sub 1 over T sub 1. And plug in all the given values, we'll get P sub 2 equals the compression ratio, which is 5, times the temperature at state 2, which is 555.77 Kelvin, and the temperature at state 1 is 295 Kelvin, times the pressure at state 1, which is 100 kilopascals, and we will get pressure at state 2 is equal to 941.98 kilopascals. And since we have all the values for the process 1 to 2, we have the pressure as well as the internal energy at state 2, temperature, and also the values for state 1. We can now solve for the pressure and temperature at state 3. So let's solve for the temperature and pressure at state 3. To solve for the temperature at state 3, we have this equation. Q sub in, or the energy input, equals U sub 3, or the internal energy at state 3 minus internal energy at state 2. So since we are looking for the temperature at state 3, therefore, using this equation, we'll find the internal energy at state 3. And rearranging the equation, we'll get U sub 3 equals U sub 2 plus Q sub in. And plug in the given values, we'll get U sub 3 equals our internal energy at state 2, 401.22 kilojoules per kilogram, plus our energy input, 350 kilojoules per kilogram, and we will get 751.22 kilojoules per kilogram. And now that we have the value for our internal energy at state 3, we can now find the value of our temperature at state 3. And we can find its value at table A-17. And looking at our property table, we can see that the internal energy at state 3 is between 0.741.98 and 758.94. So since our internal energy is between 2 points, we cannot directly again find the value of our temperature. So we'll use this equation again. M minus T over B minus T equals M minus T over B minus T, where this area is the temperature and this side is the internal energy. So plug in all the given values, we'll get our middle temperature at state 3 minus the top temperature 980 over the bottom temperature equals 1000 minus the top temperature 980 equals our middle internal energy 751.22 minus the top internal energy 741.98 over 758.94, the below internal energy, minus the 741.98, and we will get temperature at state 3 is equal to 990.9 Kelvin, and this will be the temperature at state 3. So using the same equation, we can also find the VR sub 3, and we will get V sub R3 is equal to 25.88. Now that we have the temperature, we can now solve for the pressure. To solve for pressure at state 3. So for pressure at state 3, we have the equation P sub 3 equals V sub 2 times T sub 3 times P sub 2 over V sub 3 times T sub 2. So for process 2 to 3, it is said that constant volume heat addition process. Therefore, for constant volume, our V sub 2 and V sub 3 is equal. Therefore, V sub 2 over V sub 3 will be equal to 1. We will get 1 times T sub 3, 1 times T sub 3 over T sub 2 times P sub 2. And plug in all the given values, we'll get P sub 3 equals the temperature at state 3, which is the 990.9 Kelvin, over the temperature at state 2, 555.77 Kelvin, times the pressure at state 2, which is 941.98 kilopascals, and we will get 1679.5 kilopascals, and this will be our answer for the pressure in state 3. So since we already found the values for our temperature and pressure at the end of heat addition process, we will now proceed in solving problem B, the network produced. So for the network produced, we have the equation W net equals Q in, or the heat addition, minus the Q out, or the heat rejection. So we already have the value for our Q in, which is the 350 kilojoules per kilogram, but we don't have the value for our Q out. So in order to find the value of our network produced, we need to find the value of our Q out first. So for Q out, we have the equation Q out equals U sub 4, or the internal energy at state 4, minus the internal energy at state 1. So we already have the value of our internal energy at state 1, but we don't have the value for our internal energy at state 4. So for internal energy at state 4, we need to find the value of the internal energy at state 4. We need to solve for the values in process 3 to 4. So in process 3 to 4, we have the equation V sub R4 equals V1 over V sub 2 times V sub R3. So we all know that V sub 1 over 2 is equal to R. Therefore, we get R times V sub R3. And plug in the given values, we will get V sub R4 equals our R, which is 5, times the V sub R3, which is 25.88. And calculating, we will get V sub R4 equals 129.40. And this will be our V sub R4. And since we have the value of our V sub R4, we can now find the value of our temperature and internal energy at state 4 in our property table. Using the equation m minus t over b minus t equals m minus t over b minus t, and we will get temperature at state 4 equals 556.07 Kelvin, and the internal energy is 401.45 kilojoules per kilogram. Now that we have the value of our internal energy at state 4, we can just plug in this in this equation. So plugging into our equation, we'll get Q in minus Q out, and we'll get W net equals our Q in, which is 350 minus the Q out, U4, or the internal energy at state 4, which is 401.45, minus the internal energy at state 1, which is 210.49. And we will get work net is equal to 190.96 kilojoules per kilogram. And this will be our answer in problem B. Let's proceed in solving the thermal efficiency. To solve for efficiency. For efficiency, we have the equation E equals work net over the heat addition. So we already have the values for the work net and the heat addition. So we will just plug in this into our equation, and we will get efficiency equals our work net 190.96 kilojoules per kilogram over the heat addition, which is 350 kilojoules per kilogram, and we will get efficiency equals 0.5456, or equal to 54.56%. And this will be our answer in problem C. Now, let's solve for the MEP, or the mean effective pressure. So, for the mean effective pressure, we have the equation MEP equals the network over V sub 1 minus V sub 2, which is also equal to the network over V sub 1 times 1 minus 1 over the compression ratio. So, what we need to find in order to calculate the MEP is the V sub 1. So, to find the value of our V sub 1, we'll use the ideal gas equation of state, PV equals RT. So, since we are solving for V sub 1, we'll use the pressure and temperature at state 1. So, we'll get P sub 1 times the V sub 1 equals the gas constant times the temperature at state 1. And plug in all the given values, we'll get 100 kilopascals, our pressure at state 1, times the specific volume at state 1 equals the gas constant of air, which is 0.287 kilopascals per kilopascals cubic meter per kilogram times Kelvin, times our temperature at state 1, which is 295 Kelvin, and we will get V sub 1 equals 0.84665 cubic meter per kilogram. And now that we have the value of our V sub 1, we will just plug in this into our equation. We will get MEP equals our work net, which is 190.96 over our V sub 1, 0.84665 cubic meter per kilogram, times 1 minus 1 over our compression ratio, which is 5, and we will get MEP equals 280.52 kilopascals, and this will be our answer in problem D.